And ideally, the prerequisite of this lecture is exactly the lecture given yesterday by Paolo Moras that was about the experimental setup and open problems and latest developments about the ARPES, angle-resolved photoemission spectroscopy. And indeed, so I'll try to catch up on this subject starting from a theory perspective. So let's trying to analyze the ARPES spectroscopy from many body perspective, and we'll connect this, this is a spoiler eventually, to the interacting spectral function, that is a quantity you can get out of the Green's function, that is this part here. So we'll introduce the Green's function, one particle Green's function again, having a look at the properties and especially keeping an eye on the spectral function. And eventually we would like to compute the interacting Green's function. How to do that? Via the computation of a self-energy, and the simplest, if you want, still meaningful and not toy model-like approximation to a self-energy is probably, and the most popular, is probably the GW method. So this is pretty much the menu of this talk. So let's start from ARPES. Again, here is pretty much a sketch of the experiment. You have direct photoemission where you shine light on your sample and you look at electrons getting out. Then you have inverse photoemission when electrons impinge on the substrate and you take photon out. So, and then in principle you have a number of other spectroscopies where you have here light absorption is one of them, or EELS, electron energy loss spectroscopies. So these are, let's say, macro classes of spectroscopies, and the important point from a theoretical perspective is that some of these are charged spectroscopies, meaning that electrons are either added or withdrawn from the system. So direct photoemission, we end up with a system having n-1 electrons. In inverse photoemission, we add 1 electron to the system. And this other broader class here contains also the spectroscopy that simply keep the number of the electrons in the system the same. So here we just have neutral excitation. So charge versus neutral excitations. From a theory point of view, this is a first very important discriminant when you want to look at a spectroscopy, especially because different, so charge spectroscopies require some tools, neutral spectroscopies require other tools. Let's have a look at the ARPES. This is the same picture shown yesterday. So experimentally, what can we tune here? We have incident photons that can be discriminated in terms of their energy, the angle at which they hit the surface, their polarization, and the experiment just measures the kinetic energy of the outcoming electron, ideally also completing or complementing the information, including the angle of the outcoming electrons, and as we have seen yesterday, also the spin of the electron. So we can have spin-resolved ARPES and angle-resolved photoemission. And in principle, this is the experimental tool that allows us to access experimentally the band structure. So the band structure, that is a concept that is very familiar to each of us, instead has a precise experimental counterpart that is exactly, if you want, what you can get out of the ARPES experiment. Here is a model, a cartoon. We see here a simple density of states. We have core levels, we have a valence levels with a dispersion, and this is a metal. We have a Fermi level that crosses the valence. There's then a vacuum level. So we also have access to the continuum. And here is a cartoon outcome of the photoemission experiment. For each of these, we add the photon energy. So we get peaks, discrete, though broadened out of the core levels, and then we have somehow a mirror picture of the valence that is though cut at the Fermi level, since we are extracting electrons, and we cannot extract electrons at energies larger or higher than the Fermi level. Actually, if we take more complicated versions of this experiment, we can, and the main idea is that perhaps we have a two-step, or like two photon emissions. So with the first photon, we excite electrons here, and then we do photo emissions out of the excited electron. But all of that is, let's say, state of the art, or is, I'm not going to treat those complications. But that is the main point. Also importantly, this is just a side remark about the experiment. While we think that we are actually able to compute electronic structure for any system we have in mind, experimentally, the fact that we are getting an electron out of the system means that we have to take care of charge neutrality. So if we had an insulating, hard insulator substrate, after a while we can no longer extract electrons because the system gets charged. So in these experiments, most of the time you have a metallic substrate, perhaps you have a thin insulating layer, but still, I mean, you have all these issues experimentally that of course are not there in the theory, just for us to keep in mind. And here instead is, so if this is a cartoon, this is a realistic data out of, I think these are obtained here in Trieste, the synchrotron. This is a very nice ARPES picture for system. Here is graphene adsorbed on nickel, and here you see some bands connected to graphene, but graphene on nickel is interacting. The Dirac cone is broken, so the Dirac cone should be here. This the sharp cut here is the Fermi level, so the Dirac cone should be here, is shifted here just because of the interaction between graphene and the substrate. So besides the actual physics and chemistry that happen here, this is pretty much what we can obtain out of these measurements. Okay, here is a deeper look at this point here and so on. So theoretical treatment, there are, I mean, this is very well established. Here I've listed a couple of reference papers to me, and we can start using the Fermi golden rule if we want to describe this process. So we want to describe an excitation driven by the absorption of this photon, where we have an initial state that is pretty much the ground state of the system, and a final state that is composed of an electron that is, if you want, traveling extracted from the system, ideally in a state like a plane wave-like state in vacuum, times, but in a sense of a mathematical product of within the Hilbert space, times what is left that is not meant to be the ground state with n-1, actually is a relative of an excited state at n-1. So this is the standard Fermi golden rule. We have the perturbation is the photon, and what is important here in terms of modeling is exactly how you model the final state. Here, if you want, you can also check the energy conservation is, I mean, rearranged in this way, but we have the three terms: the free electron out, the n-1 system excited, and the neutral system ground state. Here the notation that I'm going to use throughout the talk is that n is the number of particles, 0 is the ground state, and S in this form here just labels any excitation of the system at, in this case, n-1 electrons. So the final state can be written in this form here. So basically we start with a system with n-1 electron excited. We create a free electron we add a free electron in vacuum. And then we have this term here that comes from scattering theory that takes into account the fact that the process is ways more complicated. So somehow we need to take this system here and then we continue it inside so in vacuum, and then we continue it inside the system, since finding basically the proper final state, or computing photoemission by computing the proper final state, is already a task per se, something that is done in the literature. We'll see typically undergoes the name of one-step model for photoemission, but this is something that you have to calculate. And here is the physical interpretation of what happens in the process. First, this can be broken down into three pieces, and this is eventually what is called three-step model. That is, let's say, probably the simplest approach to the problem. You first think of an excitation from where like your valence band, or where your electrons sit, to some available excited states in the system. Then you have to just have this electron moving throughout the system. So you have, and by doing this, basically, it can have other mechanisms of energy loss. So somehow, pretty much as the energy loss spectroscopy. So an electron moving throughout a system that loses energies, further exciting the system itself, and then you go through the surface, and the electron is ejected into vacuum. Especially, so all of this is arbitrary, pretty much. So the actual separation of the three steps is kind of arbitrary, it's pictorial, and also I liked a lot the comment Stefano Baroni made yesterday. So it's not just giving names to things that we can actually can think we understand them. So this is just a pictorial view, and some of these are just names. Okay, and especially the split between these two processes here is not really unique. Let's just keep this in mind. And then we can make approximations on this, in particular the sudden approximation that somehow says that if the ejected electron is fast enough, it goes fast enough into vacuum, we could kind of simplify the procedure. So we can drop this term here, the scattering, the actual creation and description of the final state from the theory, and just describe our final state as this. So excited state n-1 particle plus an extra electron that is in vacuum. So this is the approximated final state. And if you do the math now, so if you compute the photoemission current, that is this, you obtain this expression here. This delta term here contains basically the matrix element with the perturbation that then will end up being squared. But here, importantly, we find an object that is theoretically very clean, that is the spectral function that is defined in this way here. So this is sum over all occupied states. In this case, there are these brackets here that I'll show you in a second, basically play the role of single particle orbitals. These are going to be called Dyson Freeman orbitals. So this is pretty much psi star, psi, psi star, and then delta. And after we'll give a more formal description of this, we'll see that this spectral function is pretty much close to, when taken diagonal, to the local density of states. Is the very many-body definition of the density of states. So we'll come to this point later, but I think this is important. We are used to think that we have single particle cartoons of the electronic structure of the systems we study. In those cartoons can be made mathematically correct when we take into account the proper definitions. So basically, single particle orbitals will become Dyson orbitals. Single particle energies will have a proper definition in terms of excitations of the many-body states, and so on and so forth. But the point is, this can be made mathematically exact in the many-body problem. Okay, so somehow this completes the picture, and from the experimental point of view, and the main quantity that ends up in our theory of the photoemission is exactly something that is related to the density of states. That indeed is more or less what we expected, because we end up with something that resembles a density of states, if you want, a density of state that is K-resolved, that are the bands, and indeed here we end up with a mathematical quantity that is exactly related to that. So let me just conclude this first part about the theoretical picture of photoemission by taking a statement from this review of modern physics from the Michelli and co-worker that is talking about ARPES, and it kind of reverses the picture we may have. So it says that ARPES has a large impact on the development of many-body theories, just because it provides information on the single particle Green's function. So somehow it's an interesting perspective to me, since typically we think that we have the Green's function and then that can help understanding photoemission experiments. Here they say that indeed the advancements on photoemission can actually help understanding what are the features you should get out of a properly defined Green's function. But the main point is that the two are tightly connected. One more comment here that anticipates some of the content of next day's lecture is that charge excitations most of the time can be treated with the one particle Green's function. We'll see that neutral excitation instead, in order to be properly treated in terms of even qualitative features, would require some treatments, namely leading to excitons that are going to be discussed in the, perhaps described within the Bethe-Salpeter, that instead need a Green's function that is the two particles Green's function, or are tightly related to the two particle Green's function. So that discriminant between charge and neutral excitation is exactly because theoretically those lead to very different methods. Okay, so let's go further in the connection with the Green's function. So let's introduce the Green's function. We have seen this yesterday already. This is the textbook definition, is the ground state expectation value of a time order product of two field operators, creation and annihilation field. Time ordering means that we have basically two contributions. For T1 larger than T2, first we create a particle in X2 and we annihilate it at X1. Vice versa, if T2 is larger than T1, we first annihilate a particle, or if you want, create a hole, evolve it in time, and then take the scalar product or the amplitude at X2. And somehow this describes this physical process where we create this electron here, evolve it in time, and then look at the amplitude. So how does this state here project onto a state that is at X1 T1 with T1 later than T2, and vice versa for the whole. So one more comment here is that this construction here may seem a bit odd at first, because why should we have this time ordering? that, okay, we kind of understand, but why should we deal with this extra complication while physically we would like just to have direct evolutions in time? That is what we really want to know about. The main point is that mathematically, time ordering is very crucial to use Wick's theorem that was introduced yesterday by Andrea Marini that eventually leads to Feynman diagrams. So the very, very reason by which we need time ordering is exactly to be able to cast the final expressions for the Green's function and the self-energy in the form of Feynman diagrams. If we were using the other related quantities like the retarded or the advanced Green's function, that simply wouldn't be, so those are typically thought or said to be more physical, like the physical response functions typically are the retarded ones, but do not lead immediately to Feynman diagrams. So this just to clarify why this extra complication here. Okay, so that expression for the Green's function is interesting, but is not effective or efficient to use. There's a very, out of the definition, basically you can immediately cast the Green's function once Fourier transformed, and in fact, while here we're in the time domain, here we are in the frequency domain, the Green's function can be cast just out of the definition in this form here. And this is also very interesting to me because this, if you're familiar with the Green's function, is pretty much the form of a Green's function of a non-interacting system. It's exactly the sum over states, product of the orbitals in X, orbital star in X prime, and then a denominator with the single particle eigenvalue. Indeed, this expression is exact, even in the many-body in a many-body formulation, if we pay the attention to defining the orbitals and the energies in this way. So energies are actually these differences between excitations at n-1 or n+1 with the ground state at n. So this is the charge excitation at n-1 electrons, charge excitation at n+1, and this is what is used for what we call occupied states, for states that are, let's say, with energies below the Fermi level, and this is the definition that we use for empty states. So somehow when we look at a spectrum, we have structures that are below the Fermi level corresponds to involve many body excitations with n-1 electrons, structures that are above the Fermi level involve excitations that are with n+1 electrons. By the way, if you want, this may have an experimental counterpart, that is, so the quantities that we put together in this density of states spectrum basically are very different qualitatively, so involve excitations n-1, n+1. So probably it's not by chance that a single experiment like photoemission can access just half of it. So photoemission just access the occupied states. Inverse photoemission, the empty states. It's true that there are experiments like STS, so scanning tunneling spectroscopy. That is the spectroscopy you do with a STM tip. It's local. You can sweep the bias from negative to positive, so you can actually access both occupied and empty states. So it's not impossible experimentally. But somehow, I mean, this fact here, I think, reflects in the fact that experimentally we may not have access to all the quantities together. And so this is for what concerns the energies, and these are the orbitals. The orbitals are just these amplitudes here, ground state, annihilation operator, and then we take the scalar product with excitation state at n-1, similarly for the empty states. These are called Freeman-Dyson orbitals. There's or also Dyson amplitudes. Probably Dyson amplitude is more popular in the chemistry community. can be computed. So there are actual works where these are computed. Those are pretty similar to the orbitals we are used to deal with, though, I mean, they carry the full many-body information. Now, importantly, so what are then the main differences between this expression here for an interacting system and for a non-interacting system? So already, just from here, we can see that these orbitals here are not orthogonal among themselves, while they are in a non-interacting picture. So in a non-interacting picture, those are just eigenvectors of a non-interacting single particle Hamiltonian. These are not normalized, second thing, except that the sum over all of them needs to integrate to the density or to the occupied ones, to the number of particles. So eventually we end up also with having many more states. This is one of the most important features. So if in a non-interacting system we have, roughly speaking, n electrons and we have n orbitals occupied, pretty much. Here we have many more orbitals, actually infinitely many more. And this is one of the main features of an interacting system. So if you want, the spectral weight is not just n Dirac deltas for n electrons, that is what you would get out of Kohn-Sham DFT or R3 Fock. We have infinitely many peaks, not normalized to one, as if the spectral weight actually would just split in multiple structures. That is the effect of these complicated many-body excitations. Actually, the number of excitations that we have in a many-body system is much larger. If you want, the size of the Hilbert space is much larger than a non-interacting counterparts. And we'll see, so this is math, we'll see the physical connection, the physical information we can get out of it. Okay. So, I've said before that what we end up having here in the spectral current, in the photoemission current is actually the spectral density that has this definition here. And now you can recognize that these guys here are really related to these guys here. Just the basis change, but this is exactly product of those Dyson orbitals there. So let's keep going. This is the same definition I've shown you before. How is the spectral function definition? This is defined. This is basically the imaginary part of the Green's function can be defined this way: G minus G dagger, properly taking into account a change of sign due to time ordering. And again, mathematically, this is the object that can be used in a Kramers-Kronig-like transform. This is also a spectral representation of the Green's function. If you want, spectral function is the mathematical source of the Green's function, okay, via this Kramers-Kronig. If you take this definition here, you plug it here, you end up with this definition here. Okay, so if you want, this is a density matrix, is a frequency resolved or energy resolved or density matrix. Okay, and if you take it local, so not x prime but just x, we obtain this that should look very familiar. This is the typical definition we use for density of states, very basic. We see probably this at very early classes in quantum mechanics. This is the proper many-body definition of the density of states. Okay, so this is a definition. How can we compute this quantity? So I'll assume you are familiar with this equation here. That is the Dyson equation for the Green's function. So somehow, if you want to compute your Green's function, you can start from the knowledge of G0, that is, in this case, is the non-interacting Green's function, where we have simply dropped the interaction. But here, in principle, we could use any reference Green's function, paying attention then to get rid of the extra potential we use here. But so this is just a side comment. But this is an exact equation for the Green's function that can be computed if we know the self-energy. This would be the third part of my talk, so just bear this in mind for the moment. Formal solution to this equation is basically operatorily this inversion here. And if we keep in mind the Lehmann representation for the Green's function, we can arrive at an expression like this. So first comment, this is true only for systems that have discrete states. So this is usually called the quasi particle equation, but this is true only when we have discrete states. I'll come back to this point later, that is mathematically subtle. But for discrete states we can. And the main point is that what is the equation obeyed by the Dyson orbitals? Well, it's pretty much a Schrödinger equation, except that basically the self-energy is here and plays the role of a potential, but the self-energy is frequency dependent, and basically each orbital feels a different potential, so feels the self-energy at a different potential that is exactly its own eigenvalue. So somehow, if you want, this is also a nonlinear problem, and so on. These are real because of discrete states, but this is, in a sense, the paradigmatic of the extra complexity you have to deal when dealing with quasi-particles or Dyson orbitals. That is that you have an orbital-dependent potential there, and that is at variance with mean field cases. Also, if you want, this is the origin of the fact that these orbitals here are not orthogonal. If you think about, basically, each S Dyson orbital obeys a different Schrödinger equation. So they are not the different eigenvectors of the same Hermitian operator. For discrete state, the self-energy is Hermitian, again, not granted in general for when you have a continuum of states, but each of them have a different, belong to a different operator, so they are not orthogonal. Okay, so this was so far the Lehmann representation. We'll see now another different representation that can undergo the name of quasi-particle, can be named as quasi-particle representation. We just start again from the formal solution of the Dyson equation. Basically, out of here, we can just look this problem as an inversion problem with a parameter, omega, so a parameterized inversion that we can cast in the form of a parameterized diagonalization problem. Okay, so omega here is a parameter. In this case, the self-energy is no longer Hermitian in general. So we need basically to, when we have a non-Hermitian diagonalization, we end up with left and right eigenvectors. Eigenvalues left, right are the same, but may be complex. Everything is labeled with omega, and if we take this inversion here out of this diagonalization, this eigen problem here, we end up with this expression that looks similar to the previous one, if you recall this, but is not the same. And the reason are, first, here we have left and right eigenvectors that are not one the complex conjugate of the other. This is more complex and actually involve, if you want, the overlap matrix to the -1 in passing from one to the other. This is standard linear algebra. We have this omega dependence, parametric, and also the omega dependence is here in in the denominator, while here we had real numbers and complex conjugate of the orbitals. So in principle, relevant poles of this expression can be obtained just taking this denominator to 0. And so if you, let me try to be a bit clearer here. This is an exact expression. So now we are trying to look at the features of these expressions, and as a main feature we would like to locate the poles of this object here. The point is that being this non-Hermitian problem, this can be complex, and so the fixed point of this denominator equal to 0, that is where the poles are, can be in the complex plane. So this expression here, basically, locally, can be described as a sum over discrete poles that are far from the real axis. Okay, while, if we look at the Lehman, if you recall, this number here is differences of total energies, so there's no way that is complex. This number here, whatsoever many body complicated system we have at hand, are real all the time, total energy differences. Okay, here is the two representations are exact. It is the way how to reconcile them. So this is the picture, if you want, the density of states, spectral function integrated, that we have out of the Lehman representation. As we said, a lot of states, okay, a feature of the many-body problem, not normalized to one, a second feature of the many-body problem, and these states kind of envelope and form structures, and these structures can locally also be described by, instead of multiple poles close to the real axis, as discrete poles far from the real axis. Okay? So if you want, these are two analytical continuation to the imaginary axis of the same object, and if we are dealing with discrete states, the two actually collapse one onto the other. That is why we can have a quasi-particle equation with the self-energy. So every single time we have a representation of the Green's function that involves the self-energy, that typically is related to this quasi-particle representation. If instead we just have the Dyson orbitals, that is related to this Lehman representation. The two basically are connected for discrete states. So somehow, if we are not in, when do we have discrete states? When we are not in the thermodynamic limit. So here, that is also interesting mathematically. The thermodynamic limit makes a mess, as very often happens. That is basically these discrete states get into a continuum, create a branch cut, and then our Green's function becomes a polydromic function. That is why basically we can have two different analytic continuations. Otherwise, the analytic continuation should be unique. Here we have two different ones, and the reason is that we have at least two branches of the Green's function. So the math gets pretty much subtle and complicated. If you really want to dig into this, there's Benham Farid, that has been probably former Cambridge professor, has written a lot of math paper on the math here. If you want to dig into the complexity of the math here, just have a look at this works here. Okay, now let's go back a bit to physics. So we've seen that in principle, if we have a self-energy, we can compute the Green's function. Let's have a look at how it looks in an interacting system. So this is the spectral function of a non-interacting system, just so one peak, sharp, Dirac delta-like. Then we put a self-energy, and here we can simplify the exercise, assuming that the self-energy is diagonal on the basis of states that diagonalize also the Hamiltonian. So this becomes a scalar problem. We can have a Taylor expansion around this point here, epsilon I, so the non-interacting given value, that is this point here. plus the real part of the self-energy. We do the Taylor expansion, and we end up with this form here of the Green's function. So this is, first, a pole that has a main structure located at capital EI, so the pole is shifted. Then we end up with a finite broadening of the pole. So here is infinitely sharp. Here we have a finite broadening, and this is really related to the imaginary part of the self-energy. This is important. Okay, so the imaginary part of the self-energy has a role, has a meaning, that is the broadening of the spectral features we get into the calculation. And then we have something that is also interesting and natively many-body, a renormalization factor. So this is not one. This renormalization factor deals with the derivative of the self-energy with respect to the frequency, so it's related to the frequency dependency of the self-energy. And so this basically says that the main quasi-particle peaks does not integrate to 1, but integrate to 0.7. Where is the extra 0.3 weight? Basically goes somewhere else, typically into a satellite structure here. Okay, so take-home message here, sharp features in the non-interacting case, shifted and broadened feature in the interacting case, with also some spectral weight due to the renormalization factor. Okay, here is the nice cartoon again, probably from the Michelli paper. So this is K-resolved, so ARP is from a non-interacting system. So K-resolved density of states. This is how it looks like in an interacting system. So we have sharp peaks close to the Fermi level, then the farther we get from the Fermi level, the broader the peaks get, the more damped, and when we reduce the spectral weight, we also need to compensate, so we have extra structures that are the satellites. Good. All of these are intrinsic features that can get already out of the spectral function or the spectral density, and are due to the dynamical, so frequency dependence, and non-Hermitian nature of the self-energy. So this extra complexity that we have in the self-energy is actually what mathematically gives the physical content of the many-body complexity. Okay, GW self-energy. So this point we have understood that the Green's functions are interesting, that they actually carry a lot of physical information that can be used to interpret experiments, but we don't actually know how to compute them in practice. And here is the last part of this talk, that is how do we get a self-energy that we can use to compute our Green's function. And a very popular approach to this comes from Edding's equation. So Eddings in 1965 introduced this equation, basically had this perturbation here, and then used a linear response approach with respect to this perturbation, what I think Andrea yesterday called the Stringer approach. That leads to this set of equations, 5 equations, self-consistently. So a set of 5 closed equations. Okay, one is the the Dyson equation that we already know for connecting G to sigma. There is also a very similar equation connecting W to P, that is the irreducible polarizability. And then we have an expression for the self-energy that involves G, W, and gamma, that is the vertex. The vertex is this object here that is pretty much related to the linear response of the Green's function itself. So this I think that G gamma G is the linear response of G itself, and this is probably the G minus 1 in the V. So it's the linear response of G minus 1. So this is really linear response. If you're familiar with time-dependent DFT is dfxc. But here the kernel is way more complicated. The kernel is the self-energy, and indeed we have the derivative of the self-energy with respect to G. So this is the linear response input into the vertex, and this enters, of course, in the linear response cast into the form of polarizability. These are closed, very difficult to solved and connected in this form here, the so-called Edding's pentagon. Mathematical note, all these Dyson's equations can be cast in the form of geometric series. This form here that you can resum, and if you sum the series, is exactly end up with the formal solution of these equations. Importantly, I tried couple of times to do this, and this works pretty well if your VP is close. So the fact that this series converges within a radius of convergence of 1 is true, and so somehow you can use this if your VP is small. Otherwise, instead, the actual Dyson equations do not suffer of this problem here. So the step in going from this contracted expression to this basically involves extra assumptions that lead you to convergence issues. So as to say, so Edding's equation can be cast in the form of Fineman diagrams, and I think that these equations being this complicated here, diagrams are very useful just to describe and to look at the topology of the equation. So which Green's function vertex is connected to which other bare or screened interaction and so on. Now, out of these equations, basically, we can immediately devise an approximation that is called GW if we drop this extra term here. So basically, these equations, there's an internal hierarchy, need to be broken somewhere if we want to start guessing some approximation. So if we drop this and we approximate the vertex just as one point, okay, that corresponds to a simple linear response for the Green's function, as if the sigma were not depending on G, okay? Basically, we have then Dirac deltas here, and this gives us immediately the polarizability written as GG, that is the probably cast in a different form, but is exactly the polarizability you would get out of a non-interacting system, whose Green's function is G, okay? And the self-energy becomes G times W. This is, Andrea yesterday introduced the GW approximation in a heuristic way, looking at the physics of the screening you get there. This is a mathematical way we can look at it. Here, in terms of diagrams, is the way it looks like, G times W. And if we take into account the geometric series for W, we have G times V, then GVV and a single bubble that is a polarizability, 2 bubbles, 3 bubbles, summed up to infinity. This is so-called RPA screening, okay? So, some messages. GW, we've seen, we have dropped part of the Edding's equation that accounts for dropping diagrams, and there are a number of diagrams that are clearly not there. And the first one that comes to mind is already the second order, and this is the second order exchange diagram. This is not there, and yesterday we were talking about self-interaction. This is the main responsible for GW not being exact in one electron cases, because this diagram is not there, and it doesn't correct for the contribution out of this diagram here. So basically we have self-screening in GW. Second thing is, in this language of Green's function and Coulomb interaction, we can write the R3-Fock as GV, and the diagram would be this. So GW is just something that is similar to R3 fog, but takes into account screening, not just static screening, dynamical screening. The two have to come together, in a sense. So if you want, is just one step, pretty complicated one. So it's in GW there's much more complication, but somehow is next step to the R3 fog. Still in terms of resemblances, GW, we saw this expansion here up to infinite order, so this is all resummed. We can see some similarities with the second-born approximation that in terms of an energy is related to, so second-born is a self-energy, but can be derived from the MP2 total energy of quantum chemistry. Okay, without self-consistency, then there are some fine details here, but if we take this MP2 total energy and the second-born self-energy, we see that the first, so this is the exchange diagram, second-order direct diagram is there, and then in MP2, we just match the second order with its exchange counterpart, so this is particle symmetric, so this is exact in one electron cases. Instead, GW keeps going with the infinite terms in the polarizability, so it's not exact. GW, on the other side, has a much better polarizability. So for systems that are very polarizable, GW is ways better than MP2. So somehow MP2 actually is used for small molecules in chemistry, and yeah. So GW works by. It's not a secret. It works very well. But as we said, issues, self-interaction is there. I've listed here a number of issues. There are a number of recent papers, even more recent than these, about how to better include vertex corrections. So vertex corrections has been a mantra in so at least since I'm looking at the GW literature. Every now and then there is a suggestion for vertex corrections. This is pretty much still an open field. So satellites in GW, we've seen that satellites are genuine features of interacting systems. Actually, they are pretty bad in plain GW. So if we do G naught, W naught without any self-consistency, they tend to be at wrong energies. If we take some self-consistency in there, basically the satellites are damped and you get this vanilla satellite that is spread all over the frequency. So they're really damped. Here the figure is difficult to read, but you can really see that if you put self-consistency in, satellites are gone. Here there's Tommaso Chiarotti's poster that has some more results on the homogeneous electron gas in this case. Similar results were also recently obtained by Crescent. I think this is Diamond, and you see in the fully self-consistent GW that is solid line. Basically the dash satellite is just gone. And this is another very interesting work on satellites by the group of Lucia Reining that just compare with recent photoemission measurements on silicon in this case, and this red here would be the position of the GW satellites that clearly you see doesn't match the photoemission position. You have to include extra terms to GW, and they do it by doing GW plus cumulant. I think that nowadays that is a pretty common beyond GW approximation. This was 2011, has been used since these days, it's very popular, and when you add cumulant on top of GW, you actually get decent positions of the satellites. Then in order to better compare with the photoemission amplitudes, you need to take properly into account the three-step model. So not just the first step, that is this spectral function, but also secondary losses, extrinsic losses, and so on, that can be modeled easily. And you get some very decent comparison. Also here, just, I mean, other recent work. Thanks.
Thank you, Andrea.